Hi everyone, my name is Piyanat. I'm a postdoc at UKZN in South Africa, and today I'm going to be talking to you about my work on 21 centimeter one-point statistic, which I mostly did during my PhD at Arizona State University with Judd Bowman and Danny Jacobs. Excuse me if there's a noise coming up. Since we just heard a nice overview from Bharat, I'm just going to jump right into the problems. There you go. So as Sam just mentioned earlier, the 21 centimeter intensity fluctuation fields is non-Gaussians. But the problem is that power spectrum, which most of the experiments are aiming to measure, is only sensitive to Gaussian signals. One way to understand is through the examples that I have here. On the left, you have a slide from semi-analytic simulation from Adam List. This is an EOR signal, and you can see the ionized bubbles here and there. They have sharp edges. And then on the right, I take the image on the left for a transform, it shuffling the phase portions, kind of like similar to what Sam just mentioned. And for a transform back, then you kind of randomize the signal here. These two maps have exactly the same power spectrum. So what this means is that either signal can result in the same power spectrum as the EOR, and saying in a different way, power spectrum cannot give you information on the non-Gaussianity. And to have that information, you need to look at other statistics. And one of the most simplest statistics that you can use to look at non-Gaussianity is the probability distribution function, the PDF, and its one-point statistic. PDF is, simply speaking, from observational perspective, it's just a histogram of the intensity fluctuation maps normalized to an integral of 1. Then one-point statistic, it's kind of like a collected term that appear in literature often, but we are probably familiar with it. You probably heard of the variance skewness and perhaps kurtosis before. These are what we call one-point statistic. And in principle, they are shape parameters of the PDF where the variance describes the spread, skewness describes the symmetry, and kurtosis describes the tailness. So let's just go into a little bit of the detail here. Skewness describes the symmetry in a way that the PDF would have a positive skewness if the distribution is leaning toward the right, or in the same way it has a long right tail, and negative skewness means the long left tail. Kurtosis will be positive if the distribution have more tail than the peak, and vice versa. And just for a note, a perfect Gaussian distribution have zero skewness and kurtosis. And in statistics, these are simply the standardized moments, statistical moment of the signal. So let's put these into the context of reionization signals. Here you have a map of the early state of reionization, 30% ionized, and you can see that the distribution is mostly Gaussian-like with small bubbles starting to form. These give rise to a Gaussian-like PDF with a long tail toward the left. And so the skewness would be negative here, will be positive here, excuse me. Oops. And during the middle of reionization, ionized bubbles starting to form. These add into the peak at the zero of the distribution. So the PDF become bimodal. And near the end of reionization, since most of the pixels are ionized, you have a lot of zeros, so you have a strong delta-like peak at zero with a long tail to the right. All of these together give you some sort of the picture like this. The reionization evolved from Gaussian-like field to very, very non-Gaussians, and the PDF changed from Gaussian light to bimodal to delta light functions, and these give rise to a very unique evolution of variance skewness and kurtosis. The variance will peak during the middle of realizations. Kurtosis will have this negative dip, very interestingly, near when the PDF become bimodal, and skewness would evolve from negative with the long tail to the left to positive with the long tail to the right. And the work that I did during my PhD is to develop realistic mock observation pipeline for HERA to forecast if we can make measurements of these statistics with HERA. I don't have time to go into the detail of this, but I just want to point out that in this result that I will be showing, there is no foreground. So we assume perfect foreground removal. Let's jump right into the result. Here on the left panel, from top to the bottom is variance, skewness, and kurtosis. Different color and light is the different build-out stages of HERA, and I want to bring your attention to the solid purple light, which is the complete HERA array. And on the right panel is the 1 sigma signal-to-noise ratios that we take into account thermal noise and sample variance. And you can see that HERA should be able to detect these statistics near the end of realizations if foreground can be removed. And that is a big if, right? Because we know that it's causing a lot of problems. So what do we do? Well, what I've been doing since then is trying to figure out if we can still measure this statistic in foreground avoidance regimes, as Sam and Dara just mentioned. The foregrounds are confined within the wedge-shaped regions inside the Fourier transform case space. So, and we can use only the data inside the foreground free, in principle, EOR window to do data analysis, making measurement in foreground avoidance. So what we did was we take the output from our previous pipeline, which take 21 centimeter simulation cube and do some gridding to form a full sky model and smoothing. And you get this map that we make a measurement. So with this map, you can stack it into an image cube and FT into K space. And then since we know exactly where the EOR, where the foreground wedge is in the K space, we can form a foreground filter or a wedge-cut filter cube, multiply it with the Fourier data cube, FT back, and you get a foreground wedge-cut image that you can make a measurement. So we done a Monte Carlo simulation of these with 500 noise cube per signal field, 20 field to mimic the sky coverage of HERA, 500 filter parameters here mean we experiment with the different extents of the foreground wedge, and you see here the leakage from window function. When you do FT, you usually apply window function to improve the dynamic range, and usually that causes the leakage of the foreground outside beyond the theoretical foreground wedge. And we found that doing a rolling style filtering works best, where you take a small chunk of the data, apply a wedge-cut filter, then we keep the central slice, which we found have the least bias, and then you roll these filters up, and eventually you can just stitch the central slices together to form these output cube that we make the measurement. And these are the result. The left panel has no filter, and on the right 4 is where some filtering happening. The horizon is where the full foreground wedge happening. The right nose is where we take extra into account the extra leakage that could happen. And here's the statistic. I'm just going to show skewness and kurtosis. There's a lot of information here, but just looking at the top row, where that would be the most realistic case that we could do. If you can control leakage, meaning if you can make it somehow the leakage disappear, you can definitely, it looks like HERA should be able to measure this statistic, especially near the end of realizations. With some small leakage, maybe you can recover something. And the same idea apply, the same pictures apply to kurtosis. What this means, what this implies that the non-Gaussian signal live in the lower K where the foreground get cut out. And it's look like if you cut the wedge, it's removed the signal, but the noise is not cut out. So how can, if we want to measure it, we either need to reduce the noise with the longer integration time or more binning, or try to figure out how to mitigate the foreground leakage outside of the wedge. So in summary, can we measure one-part statistic? Well, in optimistic sense, HERA should have enough sensitivity if we can mitigate the foreground, and that is a big if. But the question that I think I want to raise to the audience and the panelists here is it really worth to do this measurement we have limited resources in humans, and if you work on data analysis, you know that power spectrum measurement is hard enough. So can we learn more astrophysics from measuring one point statistic and also other statistics? And that is the end of my talk. Thank you.